All right, now let's calculate a single sample z-test. This is one of the t-test examples. I understand it's called a z-test, but it is more like a t-test than anything else. This is done with the specific conditions when you're comparing one sample to an overall population. It's the first logical step. And your sample size is greater than 1,000. That's what we have in this problem from the lesson. The lesson where we have this science teacher, Mrs. Thompson, who thinks her science students are considerably better than the state average. So she wants to compare the school's 1,015 students to the entire population of the state. It's a classic single sample. All right? So you're given all the information. You're given that the mean of the sample is 84.65. So this is the formula we want to use. We plug in 84.65. You're given the mean of the population, 78.71. The denominator is this standard error of the mean, which we know is simply s over the square root of n. So we know what s is from the information given us. The standard deviation is 2.58, and we know n is 1,015. So we have all the numbers we need to solve this problem. Numerator then is 5.94, square root of 1,015 is 31.86. We divide this value, you get 0.081, and we get a total z-score of 73.33. Now we don't calculate significance with a table in this format. We end up using the z-table for this. But the most important thing to know is there's a cutoff for significance based on p less than 0.05. If it's a two-tailed test, it's 1.96. If it's a one-tailed test, it's 1.64. This is a one-tailed hypothesis because Miss Thompson was predicting direction. She thought her students were better, right? And you can see they clearly are better. The z-score is a lot larger than the significant cutoff. That's how you calculate a single sample z-test.